Okay, welcome to today's astrobiology seminar. Today's speaker is Melissa Rice. She's been at Western Washington University since 2014. She is currently there as an associate professor. She did her PhD, completed it in 2012 at Cornell, and then after Cornell, she went to JPL and did a postdoc there for being hired at Western Washington. And for a number of years now, she's been working on rovers on Mars. And I sometimes hear her in video conferences when we have the science team of the Perseverance rover. So she's a familiar voice because she, apart from being involved in the camera, which she's going to tell us about, she sometimes has this other role of sort of overseeing everything as a long-term planner for the mission. Which is a job which I'm glad I don't do because it seems to be quite intensive. So anyway, she's going to tell us today about what's going on, as much as she can tell us about what's going on, because the very latest is always embargoed, but about what's happening with NASA's Mars Perseverance rover. So take it away, Melissa.
Thank you. Thanks, I'm really happy to be here and to be speaking for such an interdisciplinary crowd. Astrobiology is near and dear to my heart. It is the motivation for my work on Mars, and my interest in Mars all ties down to habitability and the potential for ancient life. And as in my postdoc, I was a NASA NAI postdoctoral fellow, and so I'm always happy to speak to the astrobiologists, even though I know nothing about the biogeochemistry that some of you do in detail. What I'm going to present for you today, I'm going to try and keep at a very high level and stay out of the weeds of the nitty-gritty spectroscopy that I do in my day-to-day, because I know this is an interdisciplinary group. But if anyone wants to geek out on the squiggly lines, please ask me questions about that in the Q&A at the end. I'll happily go there. I have been working with Mastcam-Z, which are the scientific eyes of the Perseverance rover. And I've been involved in this instrument since its start. So I'll give you an overview of the instrument, what is new and improved about Mastcam-Z from any camera that has been on Mars before. But before we get into that and the details of Perseverance's mission, what I want to do is get my clicker to work. And failing that, we'll go old school here. There we go. I want to give just a brief overview of Mars as a planet for those who may work in other parts of the solar system. Mars and the Earth have similar evolutions in their earliest periods. But the key difference between the two, when I teach solar system astronomy, is the size of Mars compared to the Earth. Size here really matters because Mars, as a smaller planet, has lost its magnetic field. And as such, it has lost much of its atmosphere to space. And so today, Mars's atmosphere is very tenuous, about 100 times the atmospheric pressure of the Earth. And so the atmospheric pressure is below the triple point of water, and we do not have liquid water on Mars today, and very little water vapor in the atmosphere. However, in its past, Mars might have been a more Earth-like world. It might have looked more like our spinning globe here, with water present as water vapor clouds, precipitation, rain, rivers, lakes, and possibly even an ocean filling the northern hemisphere of the planet. So we know that Mars was a more Earth-like place, but today it's a dry, barren, desert wasteland. However, Mars being smaller than the Earth, we still have a tremendous amount of land area to explore and a tremendous amount of outcrop surfaces to preserve this earliest period in Mars's history. If you were to take the globe of the Earth and remove all of the blue, remove the 2/3 of the surface that is covered with water, squish the continents together into a new smaller planet, it would be almost exactly the size of Mars. So the two planets have the same surface area for exploration and the same surface area recording the geologic history. So with Mars, I'm not so much interested in the Mars that is today. What I'm interested in is the rocks that are present on Mars today and what they can tell us about the period in Mars's history when the planet was a warmer, wetter world. Just how warm and how wet and for how long, we don't quite know. But the even bigger philosophical question is, in the version of Mars like this, 3.7 to 3.8 billion years ago is the time frame we're talking about, would it have been possible for Mars to have harbored life? Did it have the conditions for Mars, for life to emerge? Did it have the conditions for life to thrive and diversify? And did it have the conditions to preserve evidence for those biosignatures in the outcrops that could survive the subsequent 3.5 billion years for us to find them today? That ultimately is what I'm after. And with the Perseverance mission, we are seeking to answer that question through a very carefully selected location on the planet. I talked a bit with the students at lunch about the landing site selection process. It's a 5-year process that led us to choose Jezero crater as the single spot on the planet where we would send Perseverance to explore and ultimately bring rocks from Mars back to Earth. Now, Jezero is situated on the edge of that large impact basin, the Isidis Basin. And Jezero was chosen primarily because within that crater, there is evidence that there was once an ancient lake. And the evidence for that lake is from a river channel that snakes into the crater. And then most importantly, from this fan-shaped landform of rocks, which is the Jezero Delta, the place where the river met a lake and deposited fine-grained sediment. These are environments on Earth that are very good at preserving organic material. That's why the oil companies target these types of rocks in the Earth's geologic record for oil extraction, because they preserve those hydrocarbons very well. Now, this circle here is the landing ellipse. So the kind of estimate of where NASA would land within that, the error estimate. This white line is an estimate of where Perseverance would drive. This movie was made before Perseverance landed, so this isn't exactly the traverse we've been following, but it gives you an idea for the plan that we had going into Perseverance's mission, that we would drive up on top of the delta, around its margins, and then we would go up and out of the crater into these plains surrounding Jezero, which is where there are widespread deposits of carbonate rocks. So Perseverance's mission was always intended to be a long one in terms of distance and duration, including this traverse up and out of the crater into these plains to sample from very diverse terrains. But in the first part of the mission, we always knew that the front of the Jezero crater delta would be our prime science target. And that's because this is the evidence for the habitable environment, that long-lived lake that was around long enough for this stack of rocks to build up. You can imagine if you were to drain the Gulf of Mexico, you would be left with a Mississippi Delta that was just a big stack of fine-grained muds and rock. And that is essentially what we have preserved here. And so going to the finest grained rocks at the front of this delta, the distal portion of the delta, was always a major goal of the mission. And here's a very simple geologic map. I call this a geologic map for astronomers because we have the major units pulled out here. We have the delta shown in the green. We have in yellow at the top the remnants of another delta, a more ancient one. Its landform isn't as well preserved, but it shows us that there was another episode of deposition in this lake prior. And then we have the channel snaking into the river, into the lake on the left. And then these units mapped in red here, these were units that we saw from orbit were very olivine rich. And they had mafic materials in them, kind of primary igneous minerals. And so the team, we did not know before landing here whether these red areas, which were compositionally distinct, were sedimentary rocks maybe lake rocks deposited from these igneous minerals transported into the lake, or they might represent something else like a lava flow after the delta was deposited. So a diversity of materials here to explore. But ultimately what we're interested in is Jezero during this period, 3.5 billion years ago, roughly, when the crater was a lake. And we've seen that there's a channel snaking into the lake. That's where the delta is. But what's interesting about Jezero and distinguishes it from other crater lakes on Mars is that there's also a channel on the opposite rim of the lake, draining the water out. That's important because it means that this is not a closed system, but an open system. And it gives us some constraints on how deep the lake was. At least one period in time, there was enough water to fill the entire crater and overspill out the other side. So we know that at some point in this crater's history, it was filled to the brim with water. And we know from studying these types of lake environments on the Earth that around the margins of the lake, in the shallow marginal lacustrine environment, we get the precipitation of rocks like these. This is a sedimentary rock that is also a biosignature. There may not be organics preserved in this rock, but its morphology alone, the kind of bulbous, crinkly nature of the individual sedimentary layers of rocks here, is a telltale sign that these rocks formed and were mediated by microbial mass. And so this is a textural biosignature that tells us that when these rocks formed in an ancient lake, there was some type of biota there helping the deposition of the fine-grained sediments. So this is exactly what we're looking for in Jezero crater, especially when we get to the regions of the crater that might have been the margins of an ancient lake. We'll be looking for evidence like this, that there were microbial mats present, leading to these very unique textures in the rocks. This would be the best case scenario of something we could see on the macro scale that we could point to and say, aha, that's a potential biosignature. There are all sorts of other biosignatures we're looking for in much finer detail. Chemical biosignatures, isotopic biosignatures, and some of those biosignatures require us to get rocks from Jezero crater back into Earth laboratories in order to identify them. So what we're using to study Jezero crater is the Perseverance rover. Perseverance has a suite of instruments for scientific exploration and reconnaissance. I specifically work with Mastcam-Z, which are the two cameras, the square ones at the top of the rover's head, underneath the giant Cyclops eye, which is a laser. On the end of the rover's arm, there's another suite of instruments, including the Sherlock spectrometer and the Pixel X-ray spectrometer, of which we have a number of students and collaborators, co-Is in the room here from UW who work on Pixel. Perseverance is the culmination of decades worth of robotic exploration on the surface of Mars. And I was still in high school when Mars Pathfinder arrived, but I was fortunate enough as a graduate student to get to work in the extended missions of the Spirit rover and the Opportunity rover, the cute little solar-powered rover there on the far left. Spirit and Opportunity were really the first scientist robots on the surface. Pathfinder was, the Sojourner rover was a technology demonstration, showing that yes, we can drive cars on Mars. But Spirit and Opportunity paved the way for robotic exploration and doing spectroscopy, mineralogy, petrology on the surface of another planet. They paved the way for the Mars Science Laboratory, which is a much bigger, beefier rover, required an entirely new landing system to get that much mass safely onto the surface. And the main thing you might notice is there are no solar panels on Curiosity. That's because in the big caboose in the back, we have a nuclear power pack. We have a little pellet of plutonium-238, which decays and creates heat, which we use to charge the rover's batteries. So Curiosity is really a next generation vehicle. And Perseverance looks a lot like Curiosity. In fact, the body of the rover is almost built to print. However, the instrumentation is different. There are a few modifications to accommodate for different distributions of weight. The wheels are a little thicker because Curiosity's wheels were punctured so badly by the rocks as it drove around that we needed to beef up the wheels. But the main difference between Curiosity and Perseverance is that Perseverance has very different objectives. So Perseverance's objectives are to explore an astrobiologically relevant ancient environment on Mars. That's similar to what Curiosity did. But here in the second bullet is where things differ. Perseverance is the first rover to actively search for potential biosignatures, not just the precursors to life, but the biosignatures themselves. And Perseverance's big, new, ambitious goal is to make progress towards the return of samples to Earth. That's something that had never been attempted before. And for good reason, because it's super hard. And to get those samples back to Earth, Perseverance isn't going to do it on its own. That's why the goal was carefully worded as to make progress towards. Perseverance is the first in a 3-stage sample return campaign. So Perseverance is exploring, it's identifying the rocks that have high astrobiology potential that can tell us the most about the evolution of Mars as a planet. And it's drilling into those rocks and collecting samples for the eventual return to Earth, but Perseverance doesn't have a way to get those rocks back home on its own. That's where stage 2 comes in, which is the Mars Ascent Vehicle. This is another mission that the Jet Propulsion Laboratory is building right now that will launch to Mars, hopefully in 2028, and will carry with it a launch vehicle with fuel to take the samples from Perseverance and blast them into space. Now, it's not going to be able to carry enough fuel to get them blasted all the way back to Earth in one go. So this ascent vehicle is only going to send those samples into orbit around Mars. And that's where stage 3 comes in. There's going to be an orbiter waiting in orbit around Mars to catch those samples that the MAV launches, grab them from thin air around Mars, and transport them back to Earth. And hopefully lead them to a nice, safe landing somewhere on this planet. To give you an idea of all that's involved here, I want to show you a nice video that NASA put together of the stages of this sample return campaign. So here's what Perseverance is currently doing on the surface. Drilling into rocks that the science team identifies as high priority, and preparing for the arrival of this Mars Ascent Vehicle. Now, the baseline plan is for that vehicle to land somewhere out on the plains where it is safe for Perseverance to then drive up to it and hand off the rocks that it has been collecting. And it will seal all of those little sample cores in this fancy space bucket. And this is the best part. Watch this. So it's not the vehicle. The MAV isn't the ascent vehicle. The MAV is more like a tosser in the air. And the rocket is going to ignite at the top of its parabolic trajectory. And then it ends up in orbit around Mars. The sample return orbiter is waiting for it, rendezvous with it, captures it, seals it up, and prepares for that 100 million mile journey back to Earth. And once we get close enough, it will spit out that precious cargo for its safe re-entry into the Earth's atmosphere and landing. So this is incredibly ambitious, but incredibly important, because the only way we're going to really make progress in these big astrobiology questions about whether Mars had the necessary precursors for life and started taking steps towards the development of life, or maybe even has preserved biosignatures, we have to do that here on Earth. And we have to do that with rock samples that we select from the environments on Mars that have the highest potential for not only having been habitable, but having been inhabited, and then preserving those biosignatures for over 3 billion years. It's a tall order. This is the size of a single sample tube, kind of a whiteboard or marker. And we have 43 of those tubes on board Perseverance, which we have been filling up over the past 2 years. Of those tubes, 5 are set aside as witness samples. So we're not going to touch those, but we are going to return those to Earth. And those witness tubes will have undergone everything that the other sample tubes have undergone. And so if those witness tubes are contaminated, that tells us the level of contamination of our rock samples. So that leaves us with 38 tubes for rock and regolith and atmospheric samples. And in the role that I serve on the mission as a long-term planner, part of what I do is herd the cats of the 400-person science team to try and reach some form of consensus about which rocks that we are currently exploring are going to be worthy of a spot in one of these few limited sample tubes. And keep in mind that we have a long mission ahead of us, and we don't want to fill up all our tubes immediately, because what if we round the corner and the dinosaur bone is sticking up out of the ground from the next bed? So we have to carefully ration these sample tubes and make sure that we are preparing for future discoveries, but also doing our due diligence to capture the most relevant and interesting rock samples we encounter. And some of you may say, why go through all this effort when we have Mars rocks here on the Earth already? We have quite a collection of Mars meteorites, a good amount of diversity among them. We know that these are pieces of the Martian crust because of their atmospheric composition, teeny little gas bubbles trapped in them. We're absolutely confident from Mars. We know how old they are, and there are some hypotheses about even where on the planet they come from. The problem is these rocks that we get for free back at Earth are the rocks that are most likely to survive that interplanetary journey on their own, meaning the hard rocks, the lava rocks, the kinds of rocks that don't preserve biosignatures very well. So if we are interested in astrobiology questions, then we need to go and carefully select the soft, squishy rocks, the sedimentary rocks that are most likely to preserve those signatures. So the main differences between Perseverance and Curiosity, which it looks very similar to, are some of the design aspects, the sample caching system, which includes the turret on the rover's arm, which has the drill for it to extract rock cores. But the sample caching system is the big piece of equipment in the rover's belly that processes those sample cores, stores them in the hermetically sealed sample tubes, and gets them ready for their eventual transfer to that Mars ascent vehicle. The other thing that's different between Perseverance and Curiosity is that Perseverance is loaded with cameras, 23 cameras on the rover alone, and a lot more on the descent vehicle, watching every aspect of its landing. So in the context of 23 cameras, I only work with 2, the Mastcam-Zs, but in my unbiased opinion, these are the best cameras on the rover because they are the scientific eyes of the rover. And they're called Mastcam-Z because the Z stands for zoom. These are the first zoom lenses ever to be sent to Mars. And so Mastcam-Z is a pair of identical zoom cameras And so with 2 eyes, we can see in stereo, and we can create 3D maps of the terrain that we drive through. And that helps us for navigation and planning of the rover's traverse, but also it really helps us with the science and the 3D geometry and architecture of these rocks. Mastcam-Z also does a lot of quantitative multispectral imaging. We take a lot of pictures of this little device, which is mounted onto the rover's deck. It's our color calibration target. We know exactly what shades of blue and green and red are on here. And so when we take pictures of this thing, before we take pictures of Mars, we can calibrate exactly what the absolute reflectances are of those rocks on Mars. And so that is the kind of quantitative science that I do with Mastcam-Z. Compared to the heritage instrument, Mastcam, the main differences are that zoom capability. So if you ever look closely at Curiosity's Mastcams, kind of looks like Picasso wonky eyes. One seems small, one seems big. That's because Mastcam initially was designed to have zoom lenses, but because of budget cuts and de-scoping, the compromise was to build one eye zoomed all the way in, 100mm focal length, one eye zoomed all the way out, 34mm focal length. And so we have these 2 offsets that make stereo imaging really difficult with Curiosity's Mastcam. Mastcam-Z, on the other hand, has the 2 identical zoom lenses, which really allow us to take our imaging to the next steps. My specific expertise is with the imaging spectroscopy. And so I'm specifically interested in that quantitative color information. And not even the colors, red, greens, and blues that we can see with our naked eye, but the colors that extend into the near infrared part of the spectrum, where Mars is actually a much more colorful world. If you think about Mars in popular culture being referred to as the red planet, it really is the reddish, brownish, orangish planet, but those are the only colors that exist on the surface, maybe some grays and blacks. But when you go a little further out into the spectrum, suddenly Mars becomes a much more colorful world. So we've designed Mastcam-Z's color sensitivity to be a lot more Martian. And we have a lot more sensitivity out here in the wavelengths past 800 nanometers, where there's just more diversity, more things to see. And the way that we get all this quantitative color information is that we take pictures through a filter wheel, which is inside the camera, which only allows a narrow swath of wavelengths to pass through. And so when we take pictures, we take a series of pictures and we spin that filter wheel one position in between the pictures that we take, so that we create a stack of images, each one taken in a different wavelength. That allows us to have an image where every single pixel contains a spectrum. And so in the early days of Mastcam-Z, as a co-investigator on the team, my role was to decide exactly what wavelength positions we would use for this filter set. And we had the heritage of Mastcam, which also had filters, but we also had a lot of new knowledge about the geology of Mars and the types of mineralogies that we wanted to make sure we could detect. And so a lot of my work in the early days was running through models of different types of mineral assemblages that we might encounter on Mars with Mastcam-Z, and seeing which specific positions of wavelengths would allow us to do the most comprehensive characterization of any possible mineral suite we might find, based on what we knew about what minerals existed on Mars and which types we were likely to find. And so we added a couple of new filter positions. The Mastcam predecessor had a filter around 930 nanometers and another one a little longer than 1,000 nanometers. But there was this big gap in between where the hydration bands of a lot of the alteration minerals we were interested in wound up falling. And so everything in between these 2 red boxes, all of those minerals, I'm showing the band center of their hydration absorptions, are essentially invisible to Curiosity's Mastcam instrument. So first thing we did in the design of Mastcam-Z was slap a new band right in the middle, specifically for detecting those hydrated phases. And so this is just a little zoom in of that specific absorption feature in different types of relevant minerals that we're trying to detect at this new filter wavelength position. The other position, we added a new filter at 600 nanometers based on the spectral shape of a lot of these iron-bearing minerals. And this was another hole in the Mastcam spectrum that we were able to fill with Mastcam-Z. The other major changes to the filter set were more for atmospheric and solar imaging than for geologic purposes, but we have two new solar filters that allow us to take direct images of the sun in the relevant wavelengths. And so this is an example of some movies that were taken previously with the Mastcam instrument looking at the sun, but we now have the ability to get these types of movies in color. So over the course of my tenure at Western Washington University, most of my time has been spent in the design and then the building and testing of Mastcam-Z. And here's just a glimpse of what that filter wheel looked like before we inserted all of the individual filter positions. And then within a year, everything was assembled into this very, very early Mastcam-Z with all of its wires and guts still exposed. But it didn't take us long. By 2019, we were in the clean room with the two fully assembled Mastcam-Zs ready to go to JPL to be mounted on the rover. And we had about 5 days before we had to deliver these cameras, when we could take as many pictures as we possibly could to calibrate them. So a group of my students at the time and we went down to Malin Space Science Systems in San Diego, where the cameras were built and stored in the clean room. And you can see behind us in front of the lab sphere are the two Mastcam-Z cameras, a couple of the engineers in their bunny suits inside the clean room. We actually didn't get to go in the clean room, but we got to stare through the window, which seemed good enough. But we also got to control the cameras and take pictures. And we took several 100,000 photos working through the night for 5 days continuously to get the calibration data set for Mastcam-Z. And as a geologist who was interested in the color properties, I helped assemble what we called the geo board, which was this suite of very well-known, well-characterized color standards, and also a variety of analog rocks, and some fun things like a Lego Mastcam-Z logo that we would take pictures of at different zoom intervals with Mastcam-Z, with all of the filter sets and under different lighting conditions to understand how the camera responds in all those situations on all these different types of surfaces. And so we spent about 5 days in this control room, just taking photo after photo after photo, with headsets telling the engineers, shift the target a little to the left, change the lighting a little bit this way. And we came up with this tremendous calibration data set, which was published in 2021. And here's just a highlight of what we were able to show from that calibration data. Zooming into the center of that geoboard, where we have a piece of banded iron formation in the middle, and the white thing at the top is a piece of gypsum selenite. And with our filter set, after applying the full calibration, we were able to create this really beautiful parameter map where you can see the individual bands of hematite in that banded iron formation as just popping out at you. And we can see the hydration in the gypsum sample in the blue at the top through these different parameters. So this is what my work has been focused on leading up to Mastcam-Z's delivery and launch. But we had enough time at the end to have a little fun. And so we did a self-portrait of the team. And I actually had to fly back to Western by this point to teach a class. But the cool thing is that I still got to be in the photo because a handful of engineers, the instrument PI, Jim Bell in the middle there, were in the clean room. Rest of the team crowded around that little window, and through a number of mirrors and screens being held up, we got most of the co-Is in this photo, and I'm the blurry face up there in the upper left. So that's pretty cool. I mean, it's not photons directly bouncing off of me into Mastcam-Z, but Mastcam-Z has seen me. It's pretty cool. All right, and then Mastcam-Z got delivered to Perseverance. In January 2020, my research group and I went down to JPL so that we could look again through a window into a clean room and see Perseverance assembled with the Mastcam-Zs on top. And then we all know what happened very soon after that. And it was a miracle that in the midst of the COVID pandemic, we got to the launch pad and successfully made it off the ground within our launch window on July 30th, 2020 to Mars. Here's a shot of Perseverance landing within Jezero crater. This is taken from the Mars Reconnaissance Orbiter spacecraft. On the left-hand side here, we've got the Jezero crater delta. And then zooming in, that is Perseverance, the little bright bleb at the bottom. And on top is the parachute. And you can't see the strings connecting them, but pretty amazing that we caught that landing as it was happening. And Perseverance was loaded with cameras. It had cameras on its deck looking up, so it got to see its own landing system. And it had cameras on that sky crane looking down, so we got to see Perseverance in action as its wheels touched the surface. So I mentioned that the goal was always to study these fine-grained rocks at the front of the delta, but we didn't want to land there because it's kind of bumpy and there are dangerous cliffs. So we landed in a safe landing spot, safe parking area that we named after the author, Octavia E. Butler. And after we landed, the Mars Reconnaissance Orbiter high-rise camera took this picture, and you can see Perseverance. A little dot right there, the two bright spots are the spots where the retro rockets from the landing event blew off the dust and created a little smooth, bright area. But we also have all this debris scattered about. We've got the heat shield that detached and crashed over here. The sense stage crashed over here. And that parachute that took Perseverance safely down to the ground landed over there on the left. And then zooming in, you can see each of these in a little more detail. And keep this in your mind. We might see this again later. All right, but as a geologist, first thing I wanted to know was, what are the rocks like? This was the first fuzzy, low resolution hazard camera image we got down. But we did as much geology that we could, and we said, there are rocks there. And we didn't know if these were igneous or sedimentary, and we didn't know that for the over a year in our initial exploration. With Mastcam-Z, we started getting a lot better view of these rocks, and those two bright spots that you saw in the orbital image, you can see them here in this first panorama. These are the spots where those retro rockets blew all of the dust away. But with Mastcam-Z, we were most excited to try out the Z part of the instrument, that zoom. And this here was the closest little piece of the delta to where we landed, this isolated butte, which we think is a remnant of the delta that might have been more extensive throughout the crater in its past. And so we took a look at this little delta remnant, which was called Kodiak, and tested out our zoom capability to see how much detail we can see in those cliff faces. And we tested out our color imaging capabilities and developed these really beautiful false color stretches, incorporating wavelengths that are beyond what the human eye is sensitive to. And this was the first big science result from the mission, was based on this long distance imaging. This was over 2 kilometers away, that we could do with our zoom cameras and with the SuperCam telescope on the rover as well. But we started to do some really detailed sedimentary geology, indicating, identifying layers in this rock that were inclined, their relationship to these horizontal beds. And we started putting together the geologic story of how this delta was deposited as it was building into the lake. Zooming in a little further, which we can do with the SuperCam instrument, we can see really nice relationships and geometries of these inclined beds, how they tend to change and curve and pinch out on the lower side here, how they're truncated and flattened at the top. And I'll spare you all of the geo jargon and just show you the geology 101 version of these rocks, which is horizontal rocks below, tilted rocks below more horizontal rocks. This type of pattern, what we call bottom sets, foresets, and top sets, is the fingerprint of a river delta. And so we had the hypothesis that Jezero was a delta from orbit, but this was definitive evidence from the ground that yes, these are rocks that formed in an ancient lake. And then looking elsewhere on the delta, we started seeing these really big boulders that were embedded in the cliff face. And this giant boulder here is about 6 feet across. And to get a rock that big tumbling down a river, you need a whole lot of volume of water to move that big chunky mass. And so we started piecing together the science story of these rocks that were built in a quiet period of deposition when the lake was stable for long periods of time. And then as we move up through the stratigraphy and we start seeing these large boulder conglomerates, that's a period in time that represents a period of massive flows, huge volumes of water flooding into the crater for punctuated events. And so there's a history of lake level fluctuation and the amount of water flowing through time that we can piece even from kilometers apart like this. And this led to the first major science publication of the mission. But after we did our initial long distance imaging, surveying the land, it was time for our technology demonstration. This is a little hitchhiker that came along with Perseverance called the Ingenuity helicopter. And Ingenuity is a drone. It has a body about the size of a Washington Red Delicious apple, 4 little legs that were actually carbon fiber built in Ferndale, Washington. And some blades that are about 4 feet tip to tip. And that is a big enough wingspan for a very low mass spacecraft to generate lift in Mars's thin, tenuous atmosphere. And so flight had never been attempted, powered flight in the atmosphere of another planet before. So Ingenuity was really the first attempt, the Wright brothers moment, if you will. And Ingenuity was designed to fly 5 times. That would have been mission success for that demonstration. But Ingenuity recently completed its 50th flight, actually its 51st last week. And so NASA put together this little video of some highlights from what the helicopter's been doing over those 50 flights. Ingenuity has a little camera mounted looking down. And so it can see its own shadow as it flies around. It can also take pictures of the rocks from the air, which has been really helpful for us planning Perseverance's traverse, because we get a sneak preview of what terrain lies ahead. And there have been times when the helicopter has flown over something and we've said, yee, let's not drive over there. Those rocks look pretty gnarly. So that's an incredibly successful technology demonstration, so much so that JPL is in the process of building another helicopter, which will be part of the Mars ascent vehicle, kind of a backup to fly to Perseverance if needed and collect its rock samples and bring them back. I told you to keep that image of the parachute seen on the ground from orbit in mind, because Ingenuity flew over that crash site and captured this spectacular image of the parachute, which is just lying here for eternity on the surface of Mars, flapping in the breeze, and the back shell, which protected Perseverance during its landing. I like to say that this is a real alien landing site, except the aliens are us. But what Perseverance was really here to do was explore the rocks and select a very carefully curated sample suite for return to Earth. So the big thing that happened in the first year of the mission was the first coring and sampling activities. Here's some of the first movement of the arm, getting ready for that first drill activity. A close-up of the abrading bit. We have the ability to abrade surfaces just to get a look shallow at what is right beneath the surface dust and any weathering rinds on the rocks. And these are the types of surfaces that my colleagues in the room who work with the pixel instruments spend a lot of time looking at, because these nice cleaned off surfaces are ideal for their very small scale petrographic observations. And after we abrade those surfaces, we can do a full drill activity, drilling 6 centimeters down into the rock and extracting a rock core. Now, when we did this for the first time, everything seemed to go beautifully. After the drilling activity, you can see we created this beautiful hole in the ground with a tailings pile around it. And then Perseverance took a picture inside the sample tube before it sealed it up forever. And when we got that picture downlinked to the ground, there was no rock inside the sample tube. This was really confusing because we had a hole in the ground. There was rock missing from a hole in the outcrop, but there was no rock inside the sample tube. And so we didn't know what happened. Maybe we dropped it after picking it up and before putting it into the sample tube. Maybe it was underneath the rover somewhere. So we took the camera on the rover's arm and took pictures all under the rover's belly, nothing to be seen. Turns out the rock was a lot softer than anything we had prepared for. And in the drilling activity, the rock totally pulverized and turned into those fine-grained tailings that we saw surrounding the drill hole, and a big lump of those fine-grained tailings inside the drill hole as well. So it was actually, a little easier, the rocks being too soft than the rocks being too hard, because we can just turn some knobs on our drilling strength components and tune everything for slightly harder rock or slightly softer rocks. But we really wanted a success and we didn't want to just cut through butter again. So we spent some time driving around looking for a rock that looked like it could take a beating a little better. So we found this rock, Rochette, which was sticking up. It looked a little more competent than the rest of the flat-lying rocks around it. And we drilled and we abraded it and took some measurements of that nice abraded surface and then drilled into it. Got a close-up look at this abraded rock patch. And with some of the initial measurements from the Sherlock and pixel images, we saw that these little white spots in here were salts. And so this was our first evidence for alteration of these rocks and the potential that fluids had been flowing through these rocks and that the salts themselves might include fluid inclusions that we could study back here in Earth laboratories. That was really exciting. We spent about another year arguing about whether this and other images like it indicated a sedimentary or an igneous rock. We'll get to that in a sec. But when we took the next picture inside the sample tube, inside the drill bit, we had rock success. And we've been drilling kind of like gangbusters ever since. Here's a family portrait of all of the rocks that we have drilled into. The first 21, at least. There's one more that we've done since this slide was made. But we have a number of these different drill samples from a number of different locations on the crater floor. And we have started depositing them on the ground. So the baseline plan is for Perseverance to deliver those samples to the Mars ascent vehicle. But just in case something happens to Perseverance and it can't get there on its own, if Perseverance gets stuck in a dangerous place or something, we want to make sure that we have a backup cache someplace on the ground that we know is safe. So we identified a nice flat parking area and started dropping these little sample tubes, about half of what we had acquired at the time. So we now have 10 of these tubes dropped on the ground. And here's a nice image we took a few months ago as we were driving away after we dropped the last one. And you can see the locations of all of our different little sample tubes. This is our backup sample cache. And so hopefully this won't be the suite of rocks that makes it back to Earth. We want the rocks that are on Perseverance more, because Perseverance is going to keep collecting more and more. But if anything happens to Perseverance, we've got this in the bag as a backup. All right, I want to make sure that we give some time for questions. And so I'm going to skip forward through a lot of kind of nitty-gritty Mastcam-Z stuff and just show you some highlights of what the rocks have looked like as we've been driving around. These are rocks on what's called the Maz Formation. These are rocks in a different part of what's called the Seta Formation. And the layered structures of these had us thinking sedimentary rocks for quite a while. But the geologists on the team studied our Mastcam-Z observations, especially the ones that we took in stereo 3D, like this one. Let's see if this movie will play for us. Studying the architecture and geometries of these layered patterns, the appearance of these voids and bubbles, and put together arguments that all of this apparent layering can be explained as lava flow textures. And so ultimately, combining the geochemical evidence that we had with this Mastcam-Z imagery, we put together the case as a team that these are indeed igneous rocks. And that was a big milestone for the mission. And there are other observations that supported that, different rocks with specific lava flow textures on this part of the terrain. And this wound up being really exciting because igneous rocks, unlike sedimentary rocks, are the kinds of rocks that we can do quantitative radiometric age dating with once they're back here on the ground. So we know we're going to get the sedimentary rocks at the delta, and now we've got samples in the bag that we can get hard age dates from, and that's really important. And so I think that makes our sample cache even more valuable to get back here on Earth. Now let me skip ahead a little bit and just show you where we are now. So a lot of our activity in the recent years has been on the crater floor. And just in the past 6 months or so, we've really gone into the Delta campaign proper. But it took us a while of driving to get there. And here's a bit of a fast forward through all that driving around the crater floor. And you can see why we put our blinders on and put the pedal to the metal for a while, because we went through long stretches without really seeing outcrop until we got to the front of the delta and we started seeing these amazing cliffs with these foreset, topset truncation surfaces up close. And we started seeing a lot more details in the cliff faces of that delta, evidence for scours where little rivers had carved themselves into the flat-lying delta rocks and deposited other blocks like this big chunk of conglomerate within the delta stratigraphy. And we spent a lot of time exploring the front of the delta, looking for the finest grained sediments possible. And that's because those are the ones that have the highest potential of preserving organic material and biosignatures. So we identified these rocks at the front of the delta as our target to get drill samples of the finest grain materials possible. And here's an example of the drill holes that we made into Wildcat Ridge before we dropped all of those sample tubes on the ground. And let me finish by showing where we are today. And we'll need to wait for the science papers to come out for me to really go into the details of what we've seen in between. And honestly, the team has to figure out what we've seen in between and what all these rocks mean. But right now, Perseverance is on the edge of Belva crater. That crater is a handy scale bar. It's about exactly 1 kilometer in diameter. And the little Ingenuity helicopter is not too far away. You can see the blue pin there. So we're on top of the delta, looking at the rocks that formed most recently in the delta's deposition. And this is hot off the presses from Ingenuity's 51st flight. This is essentially where Perseverance is right now, as seen from Ingenuity from the air. That's pretty cool. And then hot off the presses from this weekend, this is our latest abrasion activity. You can see the rock that we drilled into right here on the edge of that Belva crater. Soon, we will be analyzing the composition of this rock and making a decision as a team about whether this rock is worthy of drilling into and extracting a sample from and adding to that precious sample cache. And I know that my colleagues on the Pixel team are especially eager to get their instrument on this abraded surface and help us answer that question. With that, I'm going to end, hopefully with a couple minutes for questions, and let you admire this color movie that Mastcam-Z took of the sun and Phobos's transit in front of the sun. Thank you very much.
Okay, questions for Melissa? Josh.
Thank you very much. That was a great talk. Are you guys doing any geophysical characterization of the rock? Like any mass spectrometry or anything on these things to decide whether or not they're worthy of being sent back to Earth as like a pre-characterization, or is it all the cameras?
Yeah, I'll repeat the question just for the folks watching on Zoom. The question was, are we doing any geochemical analysis, anything like mass spectroscopy, or just remote sensing camera investigations? We're doing a limited amount of what we call in situ science. That's the X-ray, XRF spectroscopy and the Sherlock-Raman spectroscopy on the end of the rover's arm. But we really don't have a way to do any more, any destructive analyses. Curiosity had a gas chromatograph mass spectrometer that was able to do isotopic measurements, to directly look for organic materials, to do gas evolution in a heated oven. But with Perseverance, we had to make the trade-offs between this really complicated sampling system that takes up a lot of the real estate on the rover itself. And that was room that meant that we just didn't have the space and the mass available to have those types of analytical instruments. So the X-ray diffraction and the SAM instrument, the evolved gas analysis that Curiosity had, are things that we just couldn't put on Perseverance. However, we're hoping to do all that and more once those rocks get back here on Earth.
So the abraded patches, we've got Pixel, which is a planetary instrument for X-ray lithochemistry, which is X-ray fluorescence, and there's 120 micron pixel size, so that's mapped, and X-ray fluorescence gives you the elements. You then have to figure out how the elements are bound together, but there are ways to do that if things are in stoichiometric ratios or other evidence from Sherlock, the Raman gives you some information. So that's the geochemical characterization, but that kind of intensity is only on the abraded patches, right? Whereas we rely on Mastcam-Z to kind of give the bigger picture with the filters that Melissa was talking about. So I'm on the Pixel team, so I just had to give it a plug.
Yeah. And we do have a laser-induced breakdown spectroscopy. That's what the laser and the big Cyclops eye on top of the rover uses. And that gives us a spectrum from which we can derive elemental compositions. And we can do that at a distance of up to 7 meters. But it has its limits.
So you got, I think, two microphones on board too. Are they still active? And if so, are you using acoustics for anything?
Yeah, there is a microphone on board as part of that SuperCam instrument that has the lids laser. And so I know that they have been listening concurrently with those laser ablation experiments, and the acoustic information of that laser ablation can give them information about the rock properties as well. And then we listen to the winds as well. And so there are scientific uses for the microphone for sure. And also it's super cool.
Andrew?
I have a question about the calibration target. You said that we know exactly what the colors are of those targets, but Perseverance has now been sitting on Mars and the sun for 2 years. If I let something out in the sun here, it gets sun bleached, right? And it change color over time. So how do you account for those changes? And then also maybe like dust deposition and stuff like that.
Yeah, absolutely. So for changes due to UV exposure, most of these materials on the calibration target have pretty high heritage from Spirit and Opportunity, and then from Mastcam. And so we have a pretty good idea about how they degrade over time. There's one pesky little piece here, a white material called aluite, that we've been watching turn more and more yellow. And we can't reproduce that in the lab under UV exposure. And so we're not exactly sure what's going on with that one. So that's being left out of our calibration pipeline for the moment. But the trickier thing, rather than UV degradation and color changes over time, is the addition of dust on the whole rover over time. And this image was taken in the first weeks of the mission. And you can see that there's kind of a brighter spot in the middle and then a darker spot around here. And right in the middle of each of these colored ships, we put a very strong magnet. And Mars's dust is actually magnetized. And so as the dust settles on the rover, it follows the magnetic field lines and gets deposited in this annulus around the magnet. So that's why we see these darker spots here, but we preserve, at least a handful of pixels that Mastcam-Z can see in that clean spot within the magnet.
The other thing is that periodically dust devils can go by and clean things off. Zach.
Thanks again for the talk. It's really cool. It's really beautiful. So you talked about stromatolites as something like this could be a biosignature that we could detect. Like if you were going to speculate, like are there other kinds of like biosignatures with the instruments that we have on Perseverance that we like could kind of wildest dreams like hope to detect, or is stromatolites that like
Yeah, I think, with the instrument I work with, Mastcam-Z, we really need these macro scale textural morphologic biosignatures. And so that would, for ancient microbial life, that would limit that to a stromatolite. Dinosaur bones sticking out of the ground is another thing. But I think as far as the rest of Perseverance's payload, the Sherlock instrument is a Raman spectrometer, and that's particularly sensitive to organic materials. And so if we abrade one of these rock surfaces and put the Sherlock instrument down, and we see a whopping organic signature, that wouldn't be a definitive biosignature, since there are many abiotic organic molecules as well. But if we saw a concentrated spike of organics in a specific situation, that would be a good hint that this could be some form of biopreservation, and it would at least lead us to collect a sample of that material and get it back here on Earth.
Just one question.
An online question.
It says, do you know what likely massive event eroded the delta leaving just that?
The question was what likely event eroded the delta, leaving just that piece? Yeah, that's a big question we have right now, is what is the erosional history of the delta, especially because we know now that the crater floor units, those rocks are igneous rocks, that there was some kind of lava flow filling the crater and covering up some areas where it looks like there had been delta extending further out into the crater before. So that puts some time constraints on the formation of the delta rather relative to these igneous units. But something had to happen to erode that delta back to its current position, leaving those little buttes and mesas behind. And with Mars, the answer is usually wind and time. So aeolian abrasion over long time scales. And these are pretty soft rocks, especially the finer grained sediments. And we've seen much more dramatic scales of erosion at Curiosity's landing site, where a sedimentary mound of rocks as tall as Mount Rainier has been eroding back over time. And so probably just those aeolian processes of the wind stripping the rocks. There are some open questions though, and one of my students, Bhavani, is looking at the distribution of the big chunky boulders that are eroding out of the delta front to help understand what the erosional history might be of the delta and how those boulders are distributed. We don't see them very far from the delta front. It would be a different thing if we saw this leg of boulders extending pretty far out into the crater. But yeah, an active question.
Don.
Your drawings show water in the lake.
The cartoons, yeah.
Was it covered with ice or is any way to tell?
That's a great question too. It's a lot easier to explain a big body of water like that in any period in Mars's history if it's covered in ice. Then we don't need as warm a temperatures, and we don't need as high of atmospheric pressures to sustain that over time. It's hard to tell. There is some analog work that's been done on delta formations under ice-covered lakes, and the sedimentary geology is very, very similar. We can't really tell from the architecture of how those layers are built, whether it was an ice-covered lake or not, but there are a few things we can look for, namely drop stones. So things that would fall through the lake from basically rocks melting out of ice rafts. And so looking for things that appear to have dropped from above and deforming the sediments underneath, those are the types of things that we're looking for. Haven't seen any yet, but keeping an eye out for sure.
Okay, well, I think it's time to draw questions to a close. So let's thank Melissa again.